All right. So we're going to continue with our lesson on 1.3. I know this is the never-ending lesson. So you had two limits for homework. The first one was the limit as x approaches 0 for sine x over x that I asked you to do the table on. What did you find was the answer? 1. That's exactly right. So from now on, we're just going to memorize this like a property. That this is a property. Anytime you see this, you know that it's equivalent to 1. And then the limit as x approaches 0 of 1 minus cosine x over x. What did you get for that one? It would have looked weird. It would have been like point something. The number should have got smaller and smaller. 0 goes to 0. So these are the two limits that you had for homework. So we're going to just we're just going to memorize these and keep these as a rule. Okay, these are a rule that we're going to use. Okay. So now, how can I take the properties of limits with these two rules that we're just going to memorize and apply them? So for instance, here's a question. So we'll call this example 1. If I have the limit as x approaches 0 of 6 sine x over x, now can you work this analytically? Can you find this answer by hand, not using the calculator? And here's the two things you need to try to do. Okay, if you can get just this limit of sine x over x, you know that's equivalent to 1. And remember, I gave you 5 properties of limits the other day. I said there's these 5 properties. They're not going to make much sense right now, but there are uses for them. So what is different in the problem I've given you and the problem that's there? What's the only difference you see?
6.
A 6. And so now the question is, can you do anything with that 6? What can you do? Since it's multiplication, the 6 can move where? Outside. So the 6 can go out of the limit. And now what you're always looking to do is basically a substitution problem. Now that I have 6 times this limit, I can now, in place of this limit, I know it approaches 1. And we get 6 times 1, which is 6. You could have also got the answer 6 by just doing a table for that, but we're trying to do it analytically, okay? Understand there what we have? All right. The next one, limit as x approaches 0. Let's say you have sine x over 2x. Okay. Same idea. How can you manipulate this and get the answer that we got? We'll call this part A. Part B. You try this one, and then I'm going to upgrade our limit rule in just a second because so we don't have a 2 in the problem, we have a what in the problem? 1/2. So the same idea, I can pull the 1/2 out times the limit as x approaches 0, sine x over x, and now I can make it that substitution 1/2 times 1, which is 1/2. Okay, that should be the answer. How can you check all these? You can say you don't have a book, you know, or if you didn't have the answer, you're doing it by hand, how can you check? Table. You make your table and check with your table, right? Okay. See what I'm doing there? All right, now, I'm going to upgrade this formula here. If, for instance, you have this problem, so let me make sure that we're clear on this. As long as the inside and the bottom both approach 0, because they're going to approach 0 at the same rate. So what I mean by that is, as I'm approaching, when I plug in a 0.1, it's going to be sine of 0.3 over 0.3. Sine of 0.03 over 0.03. As long as the inside and the bottom approach 0 at the same rate, this one still equals to 1. It doesn't change because that in here and this bottom match up. It's still going to go, those threes don't cancel, but it just approaches at the same rate. It still goes to 1. So where I'm going to upgrade our formula a little bit is, as long as the inside, if to say the inside is k times x, then the denominator has to be k times x like that. I'm not going to put a parenthesis around the bottom. But if we have sine, fix this a little bit, k times x, and you have the bottom is k times x, it still goes to 1. Okay, you can verify that with a table. So if I had the sine of the limit as x approaches 0, sine of 3x over 3x, it goes to 1. Okay. All right. So just remember that. Okay. All right. Next problem. Okay. So again, I'm trying to utilize properties to show you how I can use properties to get to these answers. Now, on this one, what is extra that we don't want? What do we wish we didn't have in there? The cosine. Yeah, if we didn't have the cosine, then the answer would be what? 1. Okay. And again, if you're going to go back to direct substitution, sine of 0 is 0, 0 on the bottom. So just remember, if you say, well, why don't you just do direct substitution? Sine of 0 equals 0. So it's going to mess everything up. So that's why I need this little shortcut. However, we have a rule in limits that says if you have multiplication, you can make it the multiplication of 2 limits. So now I can split it up into 2 limits of multiplication. And again, it's like a game. You're trying to get that just sine x over x on the inside there, okay, by itself. So now I'll highlight this limit here. What does that limit go to? Just that one. 1. So by separating this, now I know that this one goes to 1. But now the question is, how do you do the limit as x approaches 0 of cosine? Well, now we go back to the very first part of this lesson. Cosine is a wave. Looks like this. Goes forever. And at 0, it has the point, and it has curve on both sides. So thus, since it has that, you can do what? Direct substitution. So now you plug in here to get that answer. All right, so does anybody know what the cosine of 0 is? This is where you got to remember, either you can look at the graph or remember your unit circle. For the angle 0 radians, cosine is always the x-coordinate, sine is always the y-coordinate. So the cosine at 0 radian is 1. So this is 1. All right, and these two boxes that I've highlighted are multiplied. So you take each limit, you take your answers and multiply them. 1 times 1 is 1. That's your answer. Okay. All right, try one more. We'll just call this example 3. The limit as x approaches 0, 5 minus 5 cosine x over x. So now you have to ask yourself, on my two properties that we have, is this more likely to match the first property somehow or the second property? I think there's a giveaway as to which one it's going to match. And can you use properties of limits? So remember, one property we used today was if we have the limit as x approaches c of b times f of x, that can be written as b times the limit as x approaches c of f of x. You can take a constant out of a limit and multiply that by the limit, okay? So that was one property that we used. The other one was if we have multiplication of functions, f of x times g of x in the limit, you can then split that up into two limits. Limit as x approaches c of f times the limit as x approaches c of g. Those are the two properties that I've highlighted. All right. Not saying that that's what you necessarily have to use. Those are the two that we've been using. All right. So first question. I heard Tim. Do you go by what do you go by? What do you want me to call you? Okay. Which one do you think we're gonna more easily match this to? The sine one or the cosine one?
The cosine.
All right. What's the giveaway? For me, there's two giveaways.
The subtraction between the cosine and the cosine.
That's exactly right. But we can't have 5 minus 5 cosine, we gotta have 1 minus cosine. So what can we do to create a 1 minus cosine? Right here. How can I get 1 minus cosine? Anyone? Notice, we're lucky that there's a 5 here and a 5 here. Go up here. If I put a 5 in front of this, is that 5 minus 5 cosine if I distribute? Yeah, so now I can take the 5 out. So I have limit as x goes to 0. So the ability to factor expressions is very huge in calculus. As you know, last year, as your teacher, I stressed the ability of factoring on a daily basis. So now that I've factored, now this 5, if I use my property here, I have a constant multiplied. I can take that constant out. 5 times the limit as x goes to 0 of 1 minus cosine x over x. And that limit there, now we gotta be careful. It doesn't go to 1. What does that limit go to? 0. So that goes to 0. Well, 5 times 0 is still 0. But now you've shown that it's 0. Okay. And that's how you work these limits analytically. You may get some that are tougher. That we'll use that time tomorrow to ask. Tomorrow will be a question and answer day. Okay. And I'll let the folks at home that I'll pull the Zoom up for them. They can ask me questions too. So you guys at home watching this, tomorrow we'll take questions over this 1-3. Okay. So just going to have to work through. Now, again, you have 3 methods for evaluating limits. 3. What are the 3 ways that I've taught you thus far? Well, that's part of analytically. So that's more of a specific. Sometimes you can do direct substitution, sometimes you can't. Right. The first lesson I taught you 2 ways to do limits that required a calculator. What were the 2 methods? Numerically, which is a table, right? So we use tables. What else? What's the other way? You're looking at a graph if you have the graph. And now this last way is analytically, which means basically, yeah, by hand, right? Analytically. So here's the thing. Even though we're trying to work all of these by hand, you can still go back and create a table at any time that you wish. Just make sure anytime you do a table for trig functions, make sure you're in radian mode. If you're not in radian mode, your table is going to be not good. It's just going to assume you're in degrees and it's not going to correlate, okay? All right, so a check for you is always go back and make a table and be able to read the table, okay? All right. So the last bit, today, now if you are a science fan, who are my science physics fans in here? Right? You're in upper level math, you gotta be in upper level science, they go hand in hand, okay? So I wouldn't say that this is upper level science that we're about to look at, but we're gonna look at some science, maybe. Whatever you wanna call it, physics. Okay. So we have our trig limits now. I'll store these over here. They're in the video. You have it. Average and instantaneous velocity. Okay. So get where the camera can see me. This marker, I'm about to drop it. I actually don't want to drop this marker. I like this marker. This marker, I don't know this one. We'll drop this one. I'm going to drop this marker, okay? Once I drop it, it's called a free-falling body. And a free-falling body has a position equation. The height of the body, we can calculate it if we know its initial height, okay? Because a free-falling body means if it's being dropped, and then of course its path is straight down. So if we look at the vertical, this is called vertical motion that we're going to look at, the vertical motion of a free-falling object. Well, the height, and we use S of t for the height, that's the height of the body, is given by 1/2 gt squared plus v naught t plus s naught. Just write this out because this equation you'll come back to more than once. I know it looks crazy on the board, but we'll talk about what everything stands for. T, of course, is your variable. T, so S of t is your height in terms of t, where t is time in seconds. So S of t and little t are your variables. So that means G, this is read V naught, NAUGHT, or V sub 0. This is S naught, S sub 0, okay? So those are how you put, and those are constants. So G, V naught, and S naught are all constants. Let's start at the bottom. Does anybody know what S naught stands for? What does S stand for in this problem?
Height.
Height. So naught means at time 0. So this means that the 0 there means the height at the start. So that's the initial height. Okay? Guess what V stands for? Little v in science class. Velocity. This is initial velocity. All right, very good. Guess what G stands for?
Gravity.
Gravity. Acceleration due to gravity. All right, now that constant is on the Earth was one that we should memorize, okay? So now, those are what they are. Let's see their values. So on Earth, what's the acceleration due to gravity in feet per second squared? That's meters. So if we do feet, it's negative 32 feet per second squared. Okay. Negative 9.81 is meters per second squared. If we were in Canada, right, where they use meters, we would use meters, but we're in US, we use feet, so I'm going to use feet. Okay. All right. So now let's just, so there we have our problem. We have the general equation there. And so now let me pose the question, and then, so we'll call this example 1 for this. A soccer ball is dropped from the top of a 200-foot building. All right, so part A, we're going to write the position equation for the height of the ball. Then part B, we're going to find the average velocity from time t equals 1 to t equals 3. Okay? So, on both of those questions, no calculus is required. These are questions that we should be able to handle with algebra. So I'm going to go ahead and now start to sub in for those constants. All constants are given in the reading of the problem. G, V naught, and S naught. Again, we assume this building is on Earth. So now we know what the acceleration of gravity is, right? And the fact that I said is dropped tells you its initial velocity. Dropped means held and dropped. So it's starting from rest, okay, and dropped. So now if we sub in, so if we want to do part A, gravity is what? Anyone? Negative 32. I'm not going to put my units for now. T squared. B naught. What's the initial velocity if we drop the ball? 0. S naught is the initial height. What's the initial height? 200 feet. So take a second, sub that in, reduce your equation, and we're going to now take a look at what your equation is. Okay. We'll worry about average velocity in a second. Let's just get our vertical motion formula. So what happens to now this coefficient here? If it's 1/2 of negative 32, we get what? Yeah, negative 16. Had it been negative 4.9, Eli, then that would have meant we were in meters, because half of, what did you say, 9.8 is 4.9. So if you see a negative 4.9 in front of the t squared, that's an indication that it should be in meters, okay? So since the initial velocity is 0, we missed that middle term, which is good. And then we just get plus 200. And that represents the height of the ball t seconds after it's dropped. Okay, that path. So the path is what? The path of the ball is linear. However, its height is represented with what type of function is this? Yeah, quadratic, spiral. So if we're looking at this graph, for the situation, here's your 200 feet. Although the ball goes straight down, its height follows more of this. And then this right here, this is at some time. What does this stand for right here? What's that?
When it hits the ground.
When it hits the ground. Height is 0. Height is 200. Then there's the height of the ball the whole way. Okay? So we don't know when it hits the ground, 0 to something, right? Some seconds later. Okay. All right with that? So anytime you're doing any vertical motion of a projectile, so if it's fired or launched, then it has an initial velocity, but its height can always be determined with that formula. Okay? And when you're in physics, you'll talk about vectors, and you'll talk about velocity in the x direction and velocity in the y direction. As long as you have the velocity in the y direction, you can use this equation to get its height. All right? That's as far as I'm going to go with that. Now let's get to answering some questions. So what happens to the ball, wish I had a soccer ball, once it's dropped, what happens to the speed of the ball? Speeds up. Okay? It speeds up. So it starts at 0, and because of gravity, it's going to get faster and faster. So we can calculate certain speeds. One thing we can calculate is average velocity or average rate of change, which I hammered into you. Last year we talked about it in the pre-cal class, average rate of change. All right. So average velocity or average rate of change is always change in blank over change in blank. I'm leaving those blank. I want to know if you can tell me what's the blank. Average velocity or average speed is change in blank over change in blank. That's exactly right. Change in position over change in time. That's how you always get your average speed. You got to know how far did you travel and in what time did you travel in. That's how you get your average speed. All right? So symbolically for this problem, what would we call change in position? Symbolically for this problem, how would I label change in position? What letter do we use for the position or the height? What letter are we using?
Y.
No, not for this problem. There's no Y. S. And what symbol in mathematics represents change that I also taught you last year? Delta. Oh, delta. Have we used delta recently? I forgot. I can't remember. Delta S. That's change in position. Well, then, therefore, what's change in time? Okay. Just throwing that out there, right? Just adding that. But to do a change, you're gonna have how many values? How many values? Yeah, you gotta have two. You gotta have an end minus a start, right? So for this, you're gonna do S of time 2 minus S of time 1. That's your position over time 2 minus time 1. What, that right there is a fancy representation of what basic algebra concept? Well, rate of change stands for something basic in algebra. Slope. It's just slope. Okay, we'll show it in a second. So, on this problem, have I given you 2 times?
Yes.
Yes. This is now your position equation from time 1 to time 3. So now you can plug in, you know what to do here, and see if you can find the average velocity. You're gonna need a calculator, okay? Use your calculator to help you. Okay, so I'm gonna go ahead and sub in. What's my time 2? What's the second time? 3. We're doing S of 3 minus S of 1 over 3 minus 1. So we know at the end we're dividing by 2 seconds. So time interval is 2 seconds. S of 3, what did you get when you plug these in? So 9 times 16 plus that 144, negative 144 and 200. So you should have got 56, right? 56 minus S of 1 is 184. Is my work looking okay? So I got negative what? What is that? Negative 128 over 2. I got negative 64, and that would be feet per second. Is that what you guys got? Ready to check my work? Does that look okay? I'm doing it in my head, so. Ivan, how are we doing back there? Does that look, do you see what I did? Okay, all right. Okay, guess what? So now, in terms graphically, I went ahead and drew this in orange, okay? Notice, we talked about slope. We went from time 1 to time 3, and if you look at that line, we found the slope of that line to be negative 64. And of course, it's feet per second. So this secant line, remember, this was something we talked about the first day, in the first lesson, that you can find slope of secant line. But this is not got. This is not calculus. We're going to talk about calculus now. All right, so all this is just stuff we could have been doing before this point, maybe in algebra, pre-calculus, physics, and things like that. All right, so anytime you want average velocity, change in position over change in time, okay? You use that. What is my formula for vertical motion? It's this. If it's a free-falling object where the velocity, the initial velocity is 0, so it's not under any kind of power, it's not rocket propelled or anything like that, then that velocity goes to 0, and we won't have that middle term like you can see there, okay? All right. So if the object's dropped, it's always going to be negative 16t squared plus whatever the height, unless it's meters, and it's negative 4.9. Okay. All right, so now we're going to stay with this. I'm going to ask one more problem, just I have to erase. Now here's where limits help us. So it's the same problem. This is part C. Part C. Find the velocity at t equals 1 second. Not an average. Right at the 1 second mark, can we figure out what its velocity is? Okay? So, let's look at this picture and think for just a second. When I did average velocity, I needed how many points? 2 points. Okay, so this point is good here. This is 1 s of 1. We got that point. Okay, so that's done. So if we look at our formula, our second point is the 1, right? It's the, if we look at our average formula, we're going to have that second point 1. The problem is, what do I call the first point? Because I need it to just be at time 1. I can't have it at time 3. Because that's over that interval. So remember, what did we talk about? We talked about moving. Can I get this point very close to that one there without touching? Because the closer I move this point, the closer I get to the velocity at 1 second. So if I can move this second point, if I can move it real close to that point without touching, then I'm basically finding the velocity at 1 second. So this second point, I'm not going to call it 3, I'm going to call it t. Okay? I'm going to leave it as t. So this second point is t s of t. So I'm going to sub that in. And what do I want this point to do? I want this point to, do I want it to stay here? No, I want it to go close to that. So I want this t right here to get close to what? What number do I want it to get close to? 1. I want it to get close to 1, but do I want it to reach 1? How do you say get close to but don't reach? Approach. And what mathematical concept for calculus have we learned that tells you to approach something? Limits. But here's all we're going to do. Now I make this a limit and I say let t approach 1. If I try direct substitution, I mess the whole problem up. Because if I try direct substitution, look what happens. S of 1 minus S of 1 over 1 minus 1, what do I get? 0 over 0, but you get an indeterminate form. And remember your position function, it was this, negative, it's not pretty, negative 16t squared plus 200. So here's what you're going to do. This, of course, goes in place for S of t. Then plug a 1 in and see what your answer is, plug that there. Plug everything in and see if you can simplify the expression. This is practice with the problems that you got. So the first thing I want you to do, just as a checkpoint, plug this in for S of t and find S of 1, plug it in, and simplify the numerator. Let's see what you get. But is everybody with me right now? I can't do direct substitution because I'll get 0 over 0. But we have learned a method from this section on how to solve that. All right, so let's look real quick. When I sub in, I get S of t, which is negative 16t squared plus 200 minus S of 1, or when I plug in a 1, I get 184 all over t minus 1. So what should have happened in the top is you should have got 200 minus 184 will then simplify to what? 200 minus 184 is what? 16. I needed that 16, that's important. So now I have the limit as t approaches 1, negative 16t squared plus 16 over t minus 1. I would love to do direct substitution, but I know I still can't. Why can't I? It's still going to be 0 over 0. But have I taught you a technique to eliminate the whole when you have a polynomial expression? Yeah, what was the technique? Yeah, now let me give you a little bit of a hint. You can get this 16 out of the problem. The 16 can leave. This is where you apply your properties of limits. Remember the 5 that we had earlier. Remember you had a 5 minus 5 cosine. And you solved the two 5s, and you're like, well, what do I do? What did I do with the two 5s? I took both 5 and I did what? Where did I move the 5s? Factored them. First I factored, that became a multiplication, then I can move it out. So since I have a 16 and a 16, I can factor out a 16. In this case, I'm going to factor a negative 16, so it puts the minus here. Here's where your algebra skills come into play. That leaves us with t squared minus what? So if I take a negative 16 out, it leaves me with t squared minus 1 over t minus 1. And now from our properties of limits, since this is a multiplier in here, this multiplier can go to the front of the limit. So we're going to hold on to that puppy. And I'm going to go ahead and kill two birds with one stone. What should I do to the t squared minus 1? Yeah, factor, right? So it's going to factor how? How does t squared minus 1 factor? Yeah, t minus 1, t plus 1 over t minus 1. Those t minus 1's cancel. Now you can do direct substitution. You get negative 16 times 2, which is negative 32 feet per second. It's the instantaneous velocity of that object. Luckily, it's on film. You can go back and watch it. The problem is that the longer I take, the more just the upload capacity is just kind of slows it down. Okay, so just to be clear, whatever time they gave me, so let's just say I go back to this and I say, okay, I want you to now, let's just say it was part D, find the velocity at time equal to 2. Right, if it's at a specific time, that's called instantaneous velocity, not average, because it's at a specific time. So just to make sure we can do this, I need what concept to find the instantaneous, because I need to move the 2 points closer. What concept do I need then? What do I have to use from calculus to take a point and move it to the 2-second mark closely without touching? So I know this is going to be a limit. So just to make sure, if I set this up, right, it's going to set up the same way. We're not going to work it, but I'm just going to set it up the same way. So your second point, or your first point is at your 2 seconds, right? So your second point, just leave it as t, right? Leave it as t and let that point get close to this point. You follow me? So see, it's the same setup. So as the problem changes, you still set it up the same methodology. Okay, so whatever time it is, that time goes in second, or goes into this second spot, which is actually the first time. And we're moving some arbitrary point closer and closer to it without touching, so we get that. Okay. And so basically what we found is that right here on the graph, that the slope is negative 32. Now looking at the picture, does it make sense that this slope is a little shallower than this one, right? It's less steep. Okay. And think about the object. At the 1 second mark, the velocity at 1 second, it's just starting to travel. So on average, yes, it's gonna have picked up speed on average. It probably will be moving faster over those 2 seconds. Okay. I know it's a lot. You have so for you guys there, you have the video. Go back and look at this. So our concept today, we did the trig limits, and then now we're looking at average and instantaneous velocity. Instantaneous velocity requires what? What calculus concept do you need? Limits. Okay. Good job.